Welcome to another ICS Village production. The ICS Village is a non-profit organization dedicated to the promotion of industrial control system security. Visit our website at icsvillage.com to discover more about us, where to find the village, participate in our community engagement project, and how to sponsor and donate to the ICS Village efforts.
All right, good morning, folks. How's it going? Good. Everybody having fun at the HeckCon? Yeah. Yeah? All right, cool. I'm Dr. Dave Burke. I'm the CTO at Fathom 5. We are an industrial technology company out of Austin, Texas. We are really focused on how to bring modern industrial technology and like modern software development practices and modern approaches into the industrial edge of it. As part of that, we do a lot with the maritime community, and so we are actually on board ships pretty often doing various cyber sort of assessments and network assessments, trying to help improve the cybersecurity of systems. We've previously been part of Hack the Sea Village in previous DEF CONs, and this year we are part of the whole Hack the Sea Village became part of ICS Village because it's really just floating ICS components. And we are also running the CTF, the SEATF, right behind me in the next room in 316. So we actually have real maritime hardware. We've got about 17 teams now registered, and they're actually attacking the real hardware and the real OT protocols right now. So I said I would give a little talk here on MODBUS. People hear a lot about MODBUS, but I think MODBUS is also a really good example of the state of ICS, right? And security and how things can be 50 years old and still being used, and a lot of the challenges that can come with that. So a little bit about cyber test beds. We're big proponents of cyber test beds. One of our product lines is the Grace Maritime Cyber Test Beds that are over there. We have multiple consoles. Each console has a different system on it, primarily used for training. The one that you see there is the ballast console, and that I have that one up there because it actually is a MODBUS TCP implementation. And so it's 15 valves, 2 pumps, controlling a bunch of Siemens PLCs, running ladder logic, controlling it via MODBUS TCP. A little bit about, at least my view on cyber test beds. They are high fidelity and low to medium representation. And by that I mean they're high fidelity because they have the real electronics on it. I've worked in some other areas where there's virtualizations of the ICS protocols or the ICS systems, and they usually are missing something, right? They don't capture especially the repeatedness of how messages get sent out. And there's a lot of things that sort of get abstracted away that if you ever try to actually do it on the real equipment is important. Some of that makes it harder to attack, some of it actually makes it easier to attack. So when I say high fidelity, I mean that it's the real system. But by low and medium representation, the test beds, in our view, don't need to directly represent a specific ship or a specific system. So what we have on this console has four tanks, because logically, if you're doing ballast on a ship, they're starboard, they're port, they're aft and forward, right? Those are the options. Typically, commercial ships that we're on, we're usually on about 6,000 to 14,000 TEU ships. So those are big container vessels. They have between typically 12 and 16 tanks, and the tank arrangement and the ICS and systems controlling that is unique to every ship because it's sort of built into the ship, right? But so in this case we have a 4-tank system because it is the minimally representative set that you can actually train people on. And that's really what we use most of these consoles for. They're used for training people, particularly folks who have had the responsibility of doing network defense for the IT network, and they're now being told, hey, we need you to extend your defense down into the OT side. And most of those folks are like, that's great. I have no idea what the OT side looks like, right? So we provide these as mostly as training things. Most of the slide deck that I'm going to present today is actually part of what we give comes with the ballast console to train people up on MODBUS. So low to medium representation, meaning it doesn't represent a specific ship, but it's sufficient enough for a training application. In our key, it has the real OT protocols, and you can go over and see it next door. It's out over and running. They'll be attacking it, right? They get points if they can fill and drain tanks without the system knowing it, or showing that that's what they're doing. And that could be a huge safety issue, right? I mean, there's been a couple ships that have turned over because they didn't have their ballast set right. And and I guess the other piece for this is the other key on test beds is to make sure that they have a good SIM-STIM framework, so that all the systems think they're up and running. Less critical for ballast because it doesn't have a whole lot of other external connections. But when you see our navigation console, like, you actually have to stimulate a lot of the OT equipment to make it think that it's on board a ship. So we're actually giving it motion for the pitch and roll. It's actually getting dynamic GPS, which we'll get GPS in here, and AIS messages, and all those things really makes test beds come in be more useful. But really, what I wanted to talk about today was MODBUS. It is one of the de facto standards in the ICS community, and it has been for a very long time. So it was originally a client-server or master-slave configuration. We dealt with it in MODBUS RTU. RTU is the serial comms version of it. It was master and slave. And when they came back up when they modified it over to TCP, which I'll talk about in a little bit, they changed to a client-server topology, which is a little backwards from how most people would think about it when we get to the client-server. It's a message-based protocol, but it's still really a serial protocol that they've just shoved into TCP packets. So a little bit I'm going to go over is just the history, how it's used, sort of the versions, and then we'll skip through it. I'm not going to give you this whole one. It's really designed to be about an hour and a half or so brief. So I'm going to skip around in this, but the goal of this is really just to sort of give a little bit of an overview of it, and also use it as an exemplar of what some of the challenges are in the ICS community with really old protocols that just keep getting forward pushed into new systems. And by old, I mean that it actually started with Monocron, PLC company in the late 70s. And then it was proprietary at that point, and they've since been acquired by Schneider. But in the 80s, it was actually released as an open standard, and that's when it really exploded, right? And so everybody started using it. But at this point, it was a serial communication protocol. So it was usually running on MODBUS 485 or RS-485, so the multi-peer serial networks, and it was also very much in a disconnected state, right? It was that your devices were going to be physically connected to each other with serial cables and only to each other, right? And so there was really no thought about security because it was really designed to be all the components that are sitting right here, and it was really the idea that it's an air-gapped network. It's not even really a network, right? In a lot of their views, and it was really a physical security component. Because of course, if you were there physically on it, sort of all bets are off. The standard moved over to the MODBUS organization, was stood up, and in 2006, right, so you see there, it ran for about 20 years before they actually upgraded it to TCP IP. And that is what we see predominantly. So my company is on board ships pretty often, and almost guarantee that down in the bowels of the ship, in the engine room, and everything, there's MODBUS TCP running around quite a lot. And you'll see it wasn't until 2018 that they actually added MODBUS TCP security. As you can probably imagine, 2018 is when the standard for how to apply TCP security on MODBUS came out. It's really just TLS. It's really an application of how TLS gets put on it, but no one's using it, right? Because all these systems are already out there, and it's not it's a fairly cumbersome security component to put in place. It is used all over the place in terms of PLCs. Almost every PLC manufacturer out there supports it by default. If you see RTU, that's remote terminal unit, but that's the sort of smaller systems. And a lot of times it's also feeding up into the SCADA supervisory layer. On board a boat, you actually see here, we give a little example of it. You might have a MODBUS configured MODBUS system here, which has a lot of the different OT components on it for coordination.
Sorry, every PLC vendor currently uses MODBUS or is independent?
Every PLC I've used has support for MODBUS TCP. Mm-hmm. They don't always have MODBUS support for the older serial MODBUS, but I think every one I've seen has MODBUS TCP support.
For example, Siemens does adopt the
Yeah,
Modbus.
Siemens, Allen Bradley, yeah,
okay.
any of those.
Thank you.
Yeah. We used Siemens Step 7 over there. They just have a module, you drop it in, and it handles most of it for you. So any type of systems on board a boat, we just have some examples here. Everything from hatch door sensors, it's actually a really common application of it on the maritime spice. Lights, safety systems, HVAC, monitoring your batteries and the water tank, all of that would be very common on a single like MODBUS TCP network. So in the MODBUS structure, right, as we moved away from the master-slave terminology, you have a single server, which is the master, and all the other clients are the slave devices, which is a little bit weird. But the way it was originally designed is that the master would go out and do a query response. So typically you would see a configuration on the serial line where because you can only have, on MODBUS 45, you can only have one person talking at a time, right? So you have to figure out some way of doing deconfliction. It doesn't do, Ethernet comes with the back off and the deconfliction, but you have to have some way of doing the shared resourcing. You can have multiple ones talking, but you can only have one, typically one talking at a time. You have to have the protocol level to handle that. So typically the way it would work is that the MODBUS master, or the server in this case, reaches out and it goes it goes to each device. And you see a round robin pattern where it goes out and queries all the devices, then it makes decisions, and then it goes and sets new values. Right? So it's very common if you're ever looking at MODBUS, you see this like two-phase round robin approach on that. And really, even when you go to MODBUS TCP, because it's really just the serial protocol that they shoved into TCP packets, you see the exact same thing. You'll see a bunch of MODBUS, you'll see where the server actually does a bunch of MODBUS TCP queries for data, and then it usually is doing some processing and then does a bunch of writes. And I'll get into in a minute what the reads and writes are on those. The key on this is it's very hub and spoke, right? Because only the master is initiating communication, the slave responds, the slaves don't talk to each other, right, in the traditional one. Now, this got to be a bit of an issue when you start talking about the fact that they made this into TCP, because now that you're in IP and TCP framework, you can talk to each other, right? And so they actually started creating the concept of co-masters, and it gets really complicated. It's a little bit of odd structure. But from a security perspective, it also means that if you have one compromised device, that device can talk to everybody on the same subnet on there. And you may not even see that if you're only instrumented, if you have a switch, devices could talk across, within the same VLAN or subnet within that switch, and you may not even see it at the location where you might be instrumenting at the master, right? So from a cybersecurity detection perspective, that can be a lot more difficult. The odd thing I always found with MODBUS is that it actually is basically direct memory access, right? So the entire way that it works is it has, all the devices have registers of memory, and the master reads directly from the memory and writes directly to the memory on the registers. And so those are the only things you can do inside MODBUS, is you can read one register or multiple registers, and you can write one register or multiple registers. And so that also from a cybersecurity perspective gets to be very interesting, right? Because it means that there's really no security, right? Even when they add the security, the TCP security, right? That's really just point-to-point security. So if a node is still compromised on that, you can still make the write. And it's actually remarkably easy to spoof that you are the master, and then you're just writing different memory locations. And you can write the memory locations that the master then reads. Right, and so that's there's some really interesting sort of cybersecurity attacks on there. I can't get into a whole lot of the details because I actually see that we have a couple of our teams from over here, maybe hoping to see like if I give away the answers. After the event. But yeah, so it's interesting, and they also have this concept of a coil and a register. Coil is when you literally were charging a coil, right? It's going back to the analog, an analog sensor days, and it's a 1 or a 0, right? So if you ever see MODBUS, you ever see coil, that's really a Boolean, right? It's a 0 or 1. And then a register is a 16-bit value, which means they start playing games on how to do 32-bit numbers, and it's actually across multiple registers. And different vendors happen to choose whether or not they're big endian or little endian that day, as far as I can tell. So that could be another fun one on sort of the proprietary nature on that can sneak in. You can do MODBUS in a number of different versions, right? There's an ASCII version, which does a hexadecimal human readable ASCII. So it actually sends it as, the ASCII characters 0 through 9 and A through F. Which is incredibly inefficient, but is a little bit easier to be human readable. RTU is what we typically saw on the serial lines, and it's a bit packed. I have some examples of what the bit packing looks like for that. And then MODBUS TCP uses the RTU binary message format, the bit packed format, and just shoves it into a TCP packet. And then you'll see down here, we have a fireman console for firefighting, representing firefighting equipment that actually does use the MODBUS RTU over 485. And then also on that, it's often very much at very slow baud rates, right? So you're typically talking about like 9800 baud when you're talking about MODBUS RTU. So it's also very odd because you move up to MODBUS TCP, and you have a protocol that was designed for 9800 baud being used at like gigabit line speeds. Yeah, you'll see here the Ethernet, the 232, the 485, and Ethernet are the physical layer. Typically, when you get into this, the RTU, you see this sort of typical twisted pair serial connections. MODBUS Ethernet, you'll also sometimes notice in a lot of industrial applications, they don't use the RJ45 connectors for Ethernet. You may even have Canon plugs. Can I what?
Go back one slide. You went through that one.
All right. So one of the things we found is that actually a lot of the Ethernet is run on non-RJ45 connectors. Those connectors aren't great in industrial environments, and so if you're ever working in an ICS world, you may find that they're actually breaking out a lot of the pins, doing Canon plugs and stuff like that, more locking shielded connectors. Until you get to the PLC, which usually has a RJ45 jack on it. As I said before, like with MODBUS, it's really an application protocol level, and you send requests. So the server sends its request to the client, and the client responds with a response, right? So it says, I need the value in this block of registers, and then the client turns around and sends, here's that value. It typically polls the clients in a very consistent order, very often in some type of round robin or schedule. Sometimes you get ad hoc on that, but for it to be ad hoc, the server has to know that there's some triggering event. We have seen a couple where the server itself, the PLC that's the master, actually is connected to power systems or safety interlocks. So that's the other one we've seen is that when you undo a safety interlock, it changes the MODBUS protocol, which could also tell you that somebody has actually accessed a system. So the traditional MODBUS frame has 248 or 246 addresses. There's a couple reserved addresses here. We'll talk about those in a little bit. Followed by a function code, by the data, and then by a very simple checksum. And this is true for all the ASCII, RTU, and TCP, although ASCII, remember, is actually being transmitted in hex, rather than by the hex ASCII rather than the binary. So when you look at the MODBUS protocol, you'll see that in the RTU you got a 28-bit start frame. It uses 2.5 character times of silence as the separation, right? We sort of said, how do you do deconfliction? MODBUS has this interesting one. It says everybody is quiet for 3.5 characters, and a character depends on your baud rate, but it's in the order of about 15 milliseconds. Or 5 milliseconds, I'm sorry, so 3.5 characters is usually around 15 milliseconds. So if you have a silence period of 15 milliseconds, then you're starting a new frame, right? So that's sort of how it works. It's an interesting approach. You get really good at it on O-scopes and tuning O-scopes for capturing the start of frame. You get 8 bits for your station address, and you see here it starts 1 to 24s, and then it has a couple reserved. The function codes I'll go to in a little bit, but it's an 8-bit function code. Then you get 8-bit n times n words of data typically for the response. then you get a CRC in it, and then there's an end code, right? So there's a 28-bit sequence that's at the end, and then silence, right? And that's the general way. So what you see on the when they moved over to the ASCII frame, they actually just do this ASCII X3A as the start value, and then but it's all basically the same. And then the end they do it with carriage line and line as the trigger. Inside Modbus, in the devices, everything basically, we said we tell people it's like a spreadsheet, right? Because they have 4 different banks of memory, and then you can go read these different banks of memory for those. Which means that every time you touch another Modbus system, you have to figure out what the values are that are in there, right? So it takes a lot of protocol analysis to actually try to map out what all the different registers are, because for every system, what's in any individual register is just system dependent. And so you can watch this pattern, and you can watch this polling pattern and this writing pattern, but you also need to be able to observe some of the system to have some context for that. And then often this is going by very quickly in the round robin, typically in the order of every 500 milliseconds or so you have a round robin. So you also get into some big data analytics if you are doing hours and hours of capture trying to find it in terms of how do you analyze changes of the different values. I already talked about coils and registers, and then you see here these are the four sort of blocks of memory, right? And this is standard for all of the Modbus implementations. Is that you have a discrete output coils, discrete input contacts, right? And if you see discrete, right? That's so output coils are read-write. Input means read-only, right? So typically your PLC is, if it's giving you data, it's writing it into the read-only sections of the memory for the master to go retrieve, and then the master is usually writing data into the other ones for actually like setting set points or telling it to turn on a motor or items like that. And so you start with the coils, and the first 2 blocks are coils, and the second 2 are registers. You can see here it starts with the normal coils and register numbers and the addresses. That's standard, but I will tell you that every PLC vendor sort of implements that differently. So depending on what PLC vendor you're using, sometimes if you say write input coil, they'll have a value that's 00, but it actually, like, if you put in 0, what it actually puts out on the line is 10,001, right? So it actually does some of the offsets for you, and that can be pretty frustrating. But if you're monitoring it, if you're doing the observation at the actual Modbus protocol level, they're all typically very, very consistent following this pattern. So then we get into what can you do with Modbus function codes, and as I said, it's not very much, right? So this is it. You can read output coils, right? You can read input contacts. You can read the holding registers, you can read the input registers, and then you can write to those. And that's it. That is the entirety of what Modbus does, both at the TCP as well as at the serial as well as the TCP. So it's this very interesting thing of just you're writing directly, you're reading memory and writing memory directly on the device that you're working with. I have also had a lot of questions on what can you do with writing memory, right? Because as a cyber guy, anytime I'm writing memory, I have direct access to write memory into something. I always find that very interesting, right? So here's a lot of questions on how when you say write memory, how much are you writing into the real memory of the processor on the inside, which can get really interesting. There is an issue here where Modbus specification does not clearly describe bit or byte ordering. This is where I said the Indianness can be a little bit of an issue. So you do have to check the devices. So we have found, especially some Asian devices, are using a different Indianness than expected. And then as well as the different ways. So you can see here that one string, AE41 in hex, can get interpreted as 4 different ways. You sort of have to follow through on how they're handling it to resolve that. So when you're working with Modbus, we've got some examples here. So you can see here there's a request. So the request is coming from the master or the server down to the slave or the client, right? So it says here, 11 the client address, right? So that's address 17, and the function code is read coil status, and the first coil to be read is at address 13 or address 13 and hex of 19, and then an offset because it's one up in that memory bank. The total number of coils requested is 37. And then there's a CRC check, right? And so then you see a response here from address right directly below it, where you see the client address is the one responding, and it says, here's my coil status, and it tells you the number of bytes to follow. So it says, hey, here's 5 bytes, and those 5 bytes are the 37 values that were requested, and then 3 space holders to finish up the word, and then the CRC. Right, so it's a very common approach, right, where you see the master server make a request and say, hey, what do you have in this memory value, and then the system spits that back out. If you're interested from a cyber attack, it will respond to whoever is the first person to respond back, almost inevitably, right? So if you want to tell it who it is, you can respond back. Also, the systems aren't really robust on what to do if the CRC fails, right? So from a cyber perspective, if anybody steps on a message, it's very dependent on how the system is implemented on whether or not the system ever tries to retransmit or it just moves on, right? So there are some attacks. There's been some that have been breached here before, where you basically step on the response and then you send your own response, right? So there's all types of techniques like that. And then you see another one here with a input status coil where it's writing the values. And typically when you write the values, it reads the values back to you, so you can verify that it had it. Here's 2 more examples, but I'm not going to try to go through all of these examples with everybody here. A little bit about the organization. MODBUS organization was established in 2004. It's a sort of community-based organization that runs it, manages and develops the standards and the protocols, and advocates for it. Easy pros and cons. Well, it's an open source specification, so it's pretty easy for various components to be able to support it. And it's very flexible, and it's pretty easy to use. The issue is that you typically have to do all 3 RTU, ASCII, and TCP. And this intelligent peer device is basically it's not great at talking between devices. So all the data has to flow through the master for this protocol. So that is the overview. I was trying not to spend the full hour on it. Does anybody have any questions? In the back.
Do you have a word in function code 43?
Say that again?
Do you have a word in function code 43?
Function code 43. I'd have to go double check the function code for that. Which one is that?
It's the check status of the slave.
Yeah, I'd have to go back and double check on that one. I know there's a way to spoof it from what I've seen.
Yeah. It's a pretty common way if you use stuff like meter supply or something to scan the network from multiple devices.
Yeah.
You use function code 43 to check if there's any addresses.
Oh yeah, to scan through all the addresses, right?
No, it just uses specific function codes to check if there's a slave present or not.
Okay. All right. That's good. Anything else?
Yeah. From the point of view of cybersecurity, how all this schema can be, compromised. For example, if as attacker I would like to compromise to send some message to the client, from the point of view of cybersecurity, I can this environment attacked?
Yeah. So the question here is from a cybersecurity perspective, like how would the attack occur?
Yeah.
Right. So the biggest issue is that the MODBUS protocol was designed for serial communication, and once you move into an IP-based communication, you can now have devices in multiple locations, right? Or you can have a lot of other devices that are cross-connected in that same network. So we often have seen sort of business computers that are also homed on the same IP network that is doing the MODBUS TCP data on. And so now you have the ability that you could compromise one of these other devices and from there be able to send any messages you want. Because it was really designed as a serial protocol, it doesn't have any protections built into it.
No authentication.
Yeah. So and even when you have the security on it, the security is usually point-to-point security, which can help you from like just somebody connecting a new device in. But if you compromise one of those devices, especially if it's like dual owned on two networks, and you get that a lot with SCADA systems, right? You get a lot of these times where you have a MODBUS TCP network, and then you have a computer that's sitting there that's dual homed on that and the SCADA network. Right, and so it's actually grabbing, it's watching some of the data and moving some of the data over for the SCADA system. Well, if anybody compromises that system, they have full ability to go in and send any commands right to any registers within the MODBUS TCP network itself.
Okay, thank you.
Yes, that really speaks to like best practices.
Say that again.
So that really just speaks to like best practices.
It does, yeah. So the key there is, because the protocol provides no security at all, it is really important to have that well segmented off. The other thing that we've seen on a couple ones is, unfortunately, a lot of people by default run DHCP on it, and so most of the devices are static IP addressed, right? And so they are not even necessarily aware they have DHCP, and then you have like on a ship a crew member that will actually connect a device up because it's able to, and it gets an IP address. And sometimes the gateway will let you get out from that. So, trying to keep those as isolated as possible is really critical. And knowing what services you're running on the inside. Any other questions? All right. Well, thank you very much. If you want to swing over at any point, we have all the consoles up with the CTF up here next door. So, have a great time.
Thank you for joining us for another ICS Village production. Be sure to like and subscribe to the channel. Find us on icsvillage.com to become involved with our community.